We're ready, Mehmet.
Thank you, Dina. I'm Mehmet Ansoy, Vice President of Denver Astronomical Society, and we are delighted to have Dr. David Buckley as our guest speaker today. David's interest in astronomy began at an early age, and during his high school years, he became an active member of the Canterbury Astronomical Society in Christchurch, New Zealand. Dr. Buckley was the project scientist for the Southern African Large Telescope, or SALT, during the design and construction phases from 1998 to 2005, and then was appointed as the first SALT Astronomy Operations Manager, and then SALT Science Director until 2015. In 2017, he was appointed as the first South African Astronomical Observatory, or SAAO, Darrow O'Donoghue astronomer, and is currently also serving as SALT Global Ambassador. Dr. Buckley has a Master of Science from the University of Canterbury, New Zealand, and a PhD from the Australian National University. His research interest has mostly been focused on compact accreting binary stars, including X-ray binaries and catalysmic variables, which he studies with both optical ground-based facilities and UV X-ray space-based telescopes. His most recent research has focused on astrophysical transients, where he is the principal investigator of a large SALT program and a South African affiliate PI on the Vered C. Rubin Observatory, previously referred to as the Large Synoptic Survey Telescope, or LSST. Dr. Buckley has a total of 290 refereed papers with over 10,200 citations. And last year, he was appointed as an honorary research affiliate at the University of Cape Town and an affiliate professor at the University of the Free State, or UFS, one of the oldest and most respected universities in South Africa. So, Dr. Buckley, please proceed with your presentation.
Thanks very much for that introduction, Mehmet, and it's a pleasure to be speaking to you all the way here from South Africa. Yes, so I'm going to be talking about SALT, of which probably you've heard of it, or some people have heard of it, probably not the details of what it's all about and how it came to be. So part of this talk will be an introduction, first of all, to the South African Astronomical Observatory, which is the facility which operates SALT. It'll also be an introduction to the history of how SALT came about and some of the early initiatives in a sort of different route to build a large telescope in South Africa that didn't bear fruit and ended up with the SALT as we know it. And then I'm going to talk a little bit about some of the science. There's not a lot of time to do that, so I'm just going to do some highlights of the sort of scientific things that I've been using SALT to do, which is mostly to do with transient X-ray binaries and high energy phenomena. And then I'm going to finish with some view to the future, not just with SALT, but also with the plans for us to roboticize many of the telescopes in South Africa into a sort of artificial intelligence machine for the follow-up of transients. So there's quite a few different aspects to the talk, and I hope that it's of interest, and some people might find some things a little bit more interesting than others. And of course, I'll be quite happy to answer questions on anything that you might have to ask me about. And for some reason, my My PowerPoint is not advancing. Oh, that's better. Okay, so the South African Astronomical Observatory, a quick introduction to it. It was founded in early 1970s, and the headquarters are in Cape Town, and within what was originally called the Royal Observatory at the Cape of Good Hope. And this was established just over 200 years ago. In fact, we had our bicentenary last year, 2020, which, of course, because of the pandemic, was quite sadly affected. We couldn't have the sort of large public events that we had wanted to plan for. So it was, in the end, almost entirely a virtual event. SAO, as it was first established, was in the first decade or so, was run jointly with the UK government, or was jointly funded at least. And then it became an entirely South African endeavor. And it now falls under what's called the South African National Research Foundation, which is the sort of, I guess, equivalent of the NSF in the US, which funds facility for scientific access, not just astronomy, but across the whole dimensions of science. So we have about 130 staff, including about 20 PhD astronomers at present. The main observing station, of course, is not in the city. And in fact, it's at a place called Sutherland. And that's where all of our telescopes have been operating since early 1970s. And in fact, until SALT came along, there were really only 4 SAO-owned telescopes at the Sutherland site, which you can see the 4 in the picture on the top right. The turret building to the left in the distance is the old Radcliffe telescope, 74-inch or 1.9 meter telescope, which until SALT was the largest telescope on the plateau. And then the other 3 domes are the 1 meter, 0.75 meter and 0.5 meter telescopes, as it was back then. Now these have been, or at least 2 of them, have been completely refurbished. We now have a second 1 meter telescope in the middle dome, excuse me, and we have a 0.65 meter in the far dome. So Sutherland is shown on this map, just to give you an idea of whereabouts it is. It's in a region called the Great Karoo, which means thirsty land in the language of the Sun people or Bushman people who were the original inhabitants of this region. So it's a high arid plateau, good for astronomy because no one lives there. So it's one of the darkest sites on the planet, actually. It has aseasonal weather in the sense that we don't have like a monsoon season or a wet season. About 70% of the nights are usable in some manner. In other words, we can work with, say, thin cloud for spectroscopic observations, and about half the time it's completely cloud-free. It's not the best seeing site in the world, so the median seeing is only 1.3 arc seconds, and it's not the highest site either. It's 1,800 meters, but it's dry enough that we are able to do infrared observations quite successfully. So the little photos in this slide show the headquarters in Cape Town, which is about 240 miles from the main observing station. And there's a morning photo of frost at the site. You can see not much in the way of trees or anything like that. It's low, scrubby vegetation. And Cape Town, well, I don't know if any of you have visited Cape Town. I think Phil Kelton has. So this is this wonderful city. I live, in terms of this slide, way down this peninsula on the coast. But the observatory headquarters is just off to the left here. And I just want to make a plug for the fact that the IAU, the International Astronomical Union General Assembly, is going to be held in Cape Town in 2024. So I really hope some of you might decide to have a holiday in South Africa and attend that. So the Sutherland site, here's another photo from the air. And as I said, until 2005, the largest telescope was a 74-inch. Since 2002, we've added 6 telescopes in the 1 to 1.6 meter range. And later this year, we'll be installing a 1.8 meter infrared telescope. But we also have a host of other telescopes which are not our own. They're hosted for other observatories, and we have access to those. And some of those you may have heard of, like the Las Cumbres Observatory, a network of telescopes which is headquartered in California, but with observatories not only in South Africa, but Australia, Chile, Texas, Hawaii. Monet South is an observatory run by the Germans, Super WASP, a UK facility, Kelt University, I think Tennessee, Assassin is another US-based wide field transient network of small telescopes or telephoto lenses, really. Master is part of a Russian transient detection network. Meerlicht is a relatively new telescope. I'll talk more about that later. And Atlas is the most recent one, which is a NASA-funded half-meter telescope, twin to the ones that are in Hawaii that are looking for near-Earth asteroids, particularly ones that are going to impact the Earth. So you can see it's quite a collection of telescopes. These photos here show all of these various telescopes, but not SALT. I'll be showing you SALT shortly. And so here we are with SALT, and it's what we like to refer to as one of the big 5. I don't know if you've heard that term in terms of safaris and seeing game in Africa. And so the big 5 in terms of 10-meter segmented mirror telescopes are listed here. And obviously the first and the pioneers of segmented mirror telescope technology were the Keck telescopes in Hawaii. And then, of course, the Hobby Eberly telescope, for which Phil was involved for a long time, and is in a sense the sort of sister telescope of SALT. And then the 5th of the big 5, the most recently constructed, is Grantacan in the Canary Islands, which is essentially a Spanish equivalent of the Keck telescope. SALT remains the only one in the southern hemisphere. Of course, that could change. Well, it will change with the extremely large telescope that the Europeans are building. So I'm going to talk a little bit about what came before and how SALT actually came about, the beginnings of the project. And although astronomers in South Africa had quite a good reputation internationally for the science they were doing from the beginning, it was clear by the late 1980s that unless there was a new telescope of larger aperture, that we'd be essentially left behind because of the fact that there were already 4-meter telescopes, many of them around the world, and 8-meter telescopes on the horizon. And so in a review that was done of the South African astronomy scene by 2 overseas astronomers from the UK, they made this point that there was a need for what they claimed then a 3 to 4 meter class telescope. And if we had that, that would sort of keep us competitive. So Michael Feast, who was director until March 1992, had started pushing the idea of building a 4-meter telescope. And in particular, there were discussions that began with a German group at the Max Planck Institute. And when I was hired for the job that I took up at the observatory in 1991, one of the tasks that Michael Feast gave me was to work on the sort of proposal for this new 3.5 meter telescope that we called SALT, the Southern African Large Telescope. So it was going to be based on the ESO New Technology Telescope, a 3.5 meter telescope, which was a sort of pioneer of the sort of technologies that the very large telescope, the 8 meters in Paranal, were going to use. So for example, the active optics control of the thin meniscus mirror was one of the new technologies pioneered by the NTT. So following Michael Feast's retirement and the appointment of the new director, Bob Stobie, in 1992, he took forward these initial moves for a telescope. And between himself, Ian Glass, who was an astronomer on the staff of SAO, and myself, we were the 3 astronomers pushing ahead with a proposal for a 3.5 meter telescope, which would follow on the design of the NTT and would be built in not South Africa, but in our neighboring country to the north, Namibia. And the idea was that it would be built on this mountaintop called the Gamsberg, which the Max Planck Society owned and operated a small 0.75 meter telescope at the time. And so this was the original concept, which the idea was that the capital costs of the telescope would be funded by Germany, the operations, or by the Max Planck Institute. The operations of the telescope would be covered by the South Africans, and the infrastructure, putting in the road, water, power, would be funded by the Namibian government. In the end, it all came to naught for a number of different reasons. So before that, though, we went through a full sort of proposal process, design process. We took the ESO NTT design and costed it, which came out at about $27 million at that time, at the end of 1993. So what happened then was that because of the lack of interest in just a 3.5 meter telescope within the Max Planck Society, this project fell by the wayside. And the reason for that disinterest was really that astronomers in Germany were looking forward to a larger aperture telescope. And the person who'd been pushing the Gamsberg site for this 3.5 meter, El Sasser, who was the director, had retired, and with it had the enthusiasm for just another 3.5 meters. So the new director, Stephen Beckwith, was pushing forward for the Max Planck to be involved in what became the Large Binocular Telescope, which of course was built and is operating in Arizona. So after all this activity, by 1995, the 3.5 meter idea was dead in the water, and we were sort of back to square one. But what had come along in the meantime was the Hobby-Eberle telescope. And the Hobby-Eberle telescope was quite an innovation. It's a 10 meter class telescope, but built at the cost really of a 4 meter all-purpose, fully steerable telescope. The concept for the telescope came from Larry Ramsey and Dan Weidman at Penn State, but it only really became a full project once the University of Texas ran with it. And what happened in the end, of course, was the delivery of what became the Hobby-Eberle telescope. It was known as, I guess the original project, it was known as the Spectroscopic Survey Telescope. And in those days, they were circular mirrors, but of course ended up being hexagonal. So here's a slide on the Hobby Eberle telescope, and you could probably get a whole talk from Phil if you haven't already on the HET. So as I say, it was a groundbreaking sort of design. It's a restricted telescope, as is SALT, because of this innovation in the design that keeps the costs to like a fifth of the cost of the Keck telescopes. So how South Africa got involved in this was that Frank Bash, the director of McDonald, Larry Ramsey, who was the project scientist for HET, and Tom Sebring, who was the project manager, went on a sort of a road trip in the Southern Hemisphere to try and sell the idea of a Southern equivalent. And it just so happened that they gave a talk at Mount Stromlo, my alma mater, where I was spending a mini sabbatical. And after hearing their talk and chatting to them, I basically informed Bob Stobie about this possibility that maybe we can now divert from our original idea of a 3.5 meter to instead a 10 meter at the same cost. And so that's what happened. And so Bob Stobie presented the concept to the local astronomical community. Later, Bash, Ramsey, and Sebring visited South Africa. They met with key people within the, as it was, Foundation for Research Development, which was our sort of umbrella funding organization, and also key people within government and within the Department of Arts, Culture, Science, and Technology, as it was known back then, to gain support. And that finally happened, not before we had our first science meeting called Science with SALT, which I organized for March 1998 in Cape Town, which brought together potential SALT partners. It was clear that this project couldn't be funded entirely by South Africa, and that for it to succeed, we would have to convince others to come on board. And so this first meeting brought together various groups from around the world, including in the US, to come and discuss the potential of this project. So we had potential SALT partners from the US that included Rutgers University. It included HET themselves, who were coming to help present information on how the telescope was built. We had potential South African contractors, engineering firms who showed some interest in being involved in the project. And we even brought some of the HET contractors, the people who had built it in the US. So we had, for this workshop, we had a sort of parallel engineering, technical meetings and science meetings. And what came out of that was, because of the fact that the South African government had a very positive attitude for funding science, this was eventually given the nod. And I'm just quoting here some quite forward-thinking statements from the African National Congress's, the new democratic government's white paper on science and technology, where they were making these points that not to offer flagship sciences like physics and astronomy would to take a negative view of our future, that we're a second-class nation chained forever to the treadmill of feeding and clothing ourselves. And I think that was a view that a lot of our international partners thought was an amazing statement to make from a government that had so many issues to deal with, coming in to deal with the socioeconomic issues, the legacies of apartheid, to still say, yes, there's room for us to do science, obviously in areas where we can be competitive. And of course, astronomy was one of those areas. So that's the sort of landscape that we were in at the time to sort of push forward this project. And equally important was the international interest, particularly from some of our partners in the United States, who wanted to make a demonstration of commitment to helping the new democratic South Africa. And so it was the right time at the right place. So following that meeting in 1998, we spent a year starting with an interim project team, just a few of us, to start taking the HET drawings and plans, which they had kindly provided us so that we could have a step up the ladder, not have to design things from the get-go. And we also started looking more closely at exactly where we should site the telescope by undertaking much more detailed site characterization with different instruments that could measure the seeing and the meteorological conditions. And we did that over a period of 2.5 years. And we selected a final site for the telescope on the existing plateau, but a region that had somewhat better seeing conditions. And so it culminated in, well, the green light was given by government to go ahead with this project in 1999. That was when we had sufficient commitments from our partners that convinced the government that this was a viable project. And so the original partnership is shown here. You can see some of the different partners. Many of them are still partners. Some of them have withdrawn, mostly because of the difficulties that some individual universities have had with committing operations funding into the future. But of course, South Africa is now more like a 50% shareholder in the telescope. University of Wisconsin at Madison, they were originally nearly 16%. Poland, Rutgers University, Dartmouth College, they're all existing partners. Göttingen were a partner for a short time, but pulled out because of funding constraints. Similarly with the University of Canterbury in New Zealand. The UK SALT Consortium, still an active partner. The University of North Carolina, unfortunately, withdrew, but they were replaced by IUCAA, which is an Indian institution of university. Indian University, I've forgotten the acronym. And also the American Museum of Natural History is a very small partner in the SALT project. So by 2000, we had actually begun to make the first, if you like, site works at the Sutherland site. And we had the groundbreaking ceremony on the 1st of September that year, which is a photograph of it there. Some people say it was more like a ground scraping ceremony than groundbreaking because it's very hard, rocky sort of soil there. But that's when the project in earnest began. The project team were in place by that time. So I was appointed as the SALT project scientist in '98. Kobus Mering was appointed the project manager in July 1999. And between us, we hired the rest of the project team that were in place by early 2000. And here's a photograph of that project team, which you can see is a fairly small number of people. And it was added to with a few software developers and people doing drafting, design work and so on. But the project team was never a large team of people. It was always quite a small, tight team. And there they are at the groundbreaking in September of 2000. So the way we tackled the construction was to break up the telescope into its different subsystems, the sort of obvious things like the telescope tube and structure and the dome, the primary mirror system, which includes the mirror mounts, the mirrors themselves, and the whole sort of space frame, that sort of meshwork of metal which supports the mirrors. Then the tracker, which is the prime focus tracker that is used to track objects during an observation. It's quite a different way in which this telescope works compared to a conventional telescope, and I'll show more about that. Obviously, the facility building was also one big aspect of the telescope subsystems, the software, and also the payload at the prime focus that had all of the instrumentation in it. So all of these were assigned project managers who basically took full responsibility of each of those subsystems, supported with systems engineering groups, software developers, and so on. So this is a sort of a organogram showing the SALT project team, which, as I said, never got bigger than 18 people, which was by 2002. And the people who are sort of listed in that line, sort of the third line down here, were all of the project managers for the different subsystems. And of course, we had a business manager as well. And then supported by systems engineer, optical specialist, control system specialist, and then people who came and went who were like CAD people, software coding people, and so on. And then later on, software and telescope control system engineers, of which some of these people transitioned into eventually being operations staff for the telescope once it was built. So for the first year, most of the work was nothing really obvious happening, because it was basically writing requests for information, requests for proposals, doing conceptual design reviews, preparing the site. Then by 2001, the major tenders had been let and many preliminary and critical design review meetings were held. So you can see right through to 2005 was when the telescope had really come together, and we had our first light observations in the middle of that year, culminating in the completion and the dedication or opening of the telescope towards the end of that year. So this is what happened in the first year, just lots and lots of meetings, supported, I should say, by some key people internationally, and I'm just going to point some out. Hilton Lewis here is now director of Keck. At the time, he was leading the software group at Keck in Hawaii. He's actually South African, funnily enough, but has spent all his career overseas. Tom Sebring, he was the project manager from the Hobby Eberly telescope and had moved on to other projects since then. And Gary Shannon here at University of California in Davis was also a key person on the Keck telescope, and in particular to do with the optics and the mirrors and everything else, phasing and so on. So throughout the project, we managed to get a lot of support internationally. This is just one meeting, but you know, we were very, I guess, benefited from having key people helping us in this process. Although I said that the HET was like the basis on which SALT is designed, it's by no means an exact copy. And so we made some design changes, some design improvements in some cases. One of the changes was to change the elevation of the telescope by a small amount, by 2 degrees, simply to reflect the fact that in the Southern Hemisphere, one key object that we would be observing would be the Small Magellanic Cloud. And if we stuck to the original telescope elevation of 55 degrees, we would have missed part of the SMC. So we changed that. That was a fairly straightforward, trivial change in the design, but a much more significant change was the whole design of the spherical aberration corrector, and I'll talk about that later, and the coatings that we used on the mirrors. Also, the whole payload, which bears all of these science instrument, was also a completely different kettle of fish compared to HET. We had a much increased mass budget because of the desire to put, I guess, more complicated and more massive instruments up at the prime focus. We also decided to take a very aggressive view on ventilation and removing sources of heat to minimize what's called dome seeing, the sort of turbulence generated by locally produced heat sources within the telescope. Now, I just want to sort of backtrack here to give you some idea of why SALT and HET, for that matter, are so different to conventional telescopes. They're very much the analogs of the now sadly demised Arecibo radio telescope, which had a spherical primary mirror and a moving secondary that tracked objects across the sky, in this case by moving cables to move that secondary feed to follow an object as the Earth rotated. So this is the general principle, that you have a spherical mirror which creates an image plane here. As the object moves across the sky, the image moves on the spherical focal surface. And so in the case of the HET and SALT, we weren't pointing at the zenith as the case of the Arecibo, but we had it pointed at an angle to get much more sky coverage, but essentially doing the same thing, having a tracker system that moves in X and Y and in fact in Z, and all three degrees of freedom here, and the rotations about those. So this is a sort of, I guess, schematic of SALT. The main telescope tube structure here is at a fixed altitude, and all it does is rotate in azimuth. It doesn't change in altitude. So it rotates in azimuth so it can find a target, and once it's found a target, the telescope is no longer moving at all, the telescope structure here. Instead, this tracker moves the instrumentation to follow the object as it moves across. So here's a slide giving the sort of basic attributes of the telescope, which, as I say, is modeled on the HET. It's an array of 91 hexagonal spherical shaped mirror segments. We're not phasing them like in the case of the Keck telescopes, because we're not trying to get to the diffraction limit. And the mirrors are made of a low expansion glass ceramic, which in the case of the SALT telescope was sourced from a company in Russia that produced a much cheaper but just as good a product as Schott did, the company in Germany. And I'll show some pictures of the mirrors or mirror blanks from that. So we have the telescope tilted at 37 degrees from the zenith, and that gives us a declination coverage from +10 to -75 degrees. And so anything within that range, the telescope can see at some time, not all the time, but at some time. And so then the tracker follows an object across about 12 degrees of sky, and that means that you can only view things within a certain annulus on the sky. And that's all done by this very clever tracking system, which is shown here, where you have all the instrumentation mounted on what's called a hexapod or a Stewart platform, which has 6 legs, telescopic legs, that can tip and tilt the payload so that the optical axis of the payload is on a radius vector of the spherical primary mirror. So this is how it works. You can see here when the telescope tracker is at its most offset position, it's effectively a 7-meter telescope. That yellow annulus going across the mirror is the mirrors that are the only ones that are collecting light and delivering it to the focal plane. So you can see by virtue of that moving pupil that the telescope doesn't have a fixed collecting area. It has, at the worst case, equivalent of a 7-meter telescope, at the best case, the equivalent of a 9-meter telescope. So this shows the effective collecting area with time over a typical track that lasts this is like an hour, maybe nearly 2 hours. And so that means it's slightly more complicated dealing with data when you have a moving pupil. But nonetheless, this is one of the costs that you have to bear for having a telescope that's affordable in the first place, at a fifth of the cost of something like Keck. So here's this annulus that I described of the window of SALT. So anything inside that annulus can be seen by the telescope at any time. The operations team refer to this as the SALT toilet seat diagram for obvious reasons. And so basically objects over here where my cursor is are not in the field of view of the telescope. They're too far in the east. And then eventually they enter this annulus, because this is a line, this is constant declination, this is hour angle. So for this object here with the long red arrow, it can be viewed for something like 3 hours, 3.5 hours. Mid declinations, only maybe an hour, rising and setting. Southern declinations, up to 6 hours. So this is, something which is obviously a restriction, but it's something which, for the sort of science that we do, is not significantly, a showstopper. It does mean we can't observe things continuously all night long, unless they're at favorable declinations where we can get a few hours. So, of course, the consequence of this is that the telescope is not operated like other conventional telescopes where astronomers go up and have the telescope for a couple of nights and observe their objects. Instead, this is an entirely Q-scheduled telescope, 100% Q-scheduled, 100% service observing. So we employ staff astronomers who undertake the observations each night. And typically in any given night, we might have 10 or so, 5, 10 that are observed in a given night, all with different targets and all with different instruments, depending on what the programs are. These are some of the attributes of the telescope. It's designed to not degrade the best seeing that we can expect at the site. I told you it's 1.3 arc seconds median seeing, but we do have sub-arc second seeing from time to time. But basically the whole image quality of the telescope that includes the primary mirror and the secondary optics is designed to deliver the energy within the point spread function of a point source, 80% of the energy within 0.9 arc seconds. And it's optimized to work also from the blue, from the ultraviolet cutoff of the atmosphere out to 1.7 microns. It has an 8 arc minute diameter field of view. This is twice as big as what HET was. This was as a consequence of the redesign of the spherical aberration corrector. So here are some of the design changes that we made, which has improved the performance of SALT over the original HET design. Most of it comes into the improved design of the spherical aberration corrector that I'll show in a moment, and the use of efficient combinations of silver and aluminium multi-layer coatings that were delivered by Lawrence Livermore National Labs for these mirrors. Also, in the optical design, we changed the pupil diameter to 11 meters, which gave us an effective 15% increase in the light gathering power as well. And then the other innovations were alluded to. It was like the payload is a much larger entity. It can have a much larger mass budget for instrumentation. So we ended up with much more capable instrumentation in terms of low to medium resolution spectroscopy than the original HET, although of course HET has now been repurposed significantly and has sort of jumped another step in that regard. So I'm just going to quickly talk about the spherical aberration in SALT. As you probably all know, you have to have a parabolic primary if you want the rays all to come to the same focus from objects at different paraxial angles. And if you use a spherical mirror, then the rays that come from the outer part of the mirror come to a different focus compared to the rays that come from the inner part. And so if we didn't correct for this, the best images we could get with SALT would be 10 arc minutes, which is like useless, a third of the diameter of the moon. A star would be that big. So what was employed on the HET was a 4-mirror spherical aberration corrector shown at the top. And the one that's used in SALT is also 4 mirrors, but a completely different design, which has enabled us to have much better imaging quality. You can see spot diagrams here from the optics ray tracing, where these are 1 arc second boxes and for different field angles. And you can see that the image quality is significantly better than in the HET design. And I'm not doing this to diss the HET. What we had was the luxury of a year and a half to do a completely new design study, whereas the HET SAC had to be designed very quickly once their 2-mirror option was not going to work. So it just shows you that, you know, doing something where you have the luxury to spend time on design is sometimes really important to do. So I'm going to show now some slides of the construction. This is what the site looked like before work began. And 2 years after the groundbreaking, the main facility building and dome was done. The dome was installed, the building itself with the ventilation louvers you can see there was completed. And then the mirror and mirror support truss, this red space frame, a very stiff but lightweight structure to support the mirrors, decoupled from the main gray structure of the telescope tube, so that there were no sort of forces, stresses transferred through to the mirrors. So it's a kinematically mounted structure on top of the mirror mount. And the whole thing, as I say, rotates in azimuth only. These are the mirror mounts. These were designed and built by a company called EOS Technologies, which was an Australian-based company, but with offices in Tucson. And in fact, it was the Tucson factory that produced the initial mirror mounts for SALT. And then once they were proven, the rest of them were all produced by local engineering companies in South Africa. So these are the mounts that support the individual hexagonal mirrors, and they have worked incredibly well. They have no hysteresis. They're a very nice system. They have actuators, 3 per mirror, that allows the mirrors to tip and tilt and to be aligned properly. These were, well, this shows a photo of one of the first blanks that was delivered. So the blank material was sourced, as I said, in Russia. The mirror blanks were sent to as they were known then, Eastman Kodak in Rochester, and they did the mirror figuring and ion figuring to produce the final product before it was sent to South Africa and coated in our own coating chamber with aluminium coating. And that shows one of the mirrors being lifted out or into the telescope after it had been recoated. Then the prime focus tracking system was installed through the dome opening. This is the whole sort of gantry on which the prime focus instrumentation has to move in X and Y. And there you can see it at the top of the telescope with the prime focus tracker with the payload. So these are all the main parts of the telescope that you can see highlighted here. This is the details of the top end, which has this hexapod system that carries the instruments, which in this case, the main instrument is the spectrograph at the top. Buried inside here are also other instruments now, the acquisition and fast imaging camera and the fiber instrument feed. And then finally, the mirrors, final mirrors came and were installed in May 2005. And this is the final populated primary mirror array. We'd been able to get first light actually the year earlier than this, when we only had a subset of about 7 of the mirrors. And as more and more mirrors arrived, we put them in and continued with testing the telescope's performance. And then finally, the software and control systems all came together. And as I say, SALT is a 100% Q-scheduled serviced observing telescope. It's run by 2 people each night, a SALT astronomer and a SALT operator. During COVID, we actually were closed, I think, for 3 weeks until we were able to do complete remote observing from Cape Town, which is still actually sort of 50-50. We do remote or on-site observations. I'm going to quickly talk about some of the SALT instruments because I want to show you some signs from these. So these are the 3 facility instruments that are on SALT. The first 2 were the first light instruments that were delivered at the time the telescope was completed in November 2005. The main one is the prime focus instrument shown here being lifted by a crane onto the top of the platform, the prime focus platform. And this is a very complex instrument. It has something like 6 different diffraction gratings that can be swapped in and out to give low to medium resolution spectroscopy and covering different wavelength regions. The detectors can be run at very high frame rates, so we can do sampling at 1/10 of a second. So this has been quite an innovation to do fast spectroscopy. We have a polarimeter, so we're able to do both imaging and spectropolarimetry, and we have Fabry-Perot etalons, which allow us to do narrowband imaging spectroscopy. This instrument was conceived and built at the University of Wisconsin. Ken Nordziak was the PI for that instrument. Then in South Africa, we built at the SAO Salticam, which is a fast imaging camera exploiting the full field of view of the telescope with multi-filters, able to do fast photometry and quite deep photometry. And then the final instrument, which was not delivered at first light because there was some delay in its funding and development, was eventually built at the University of Durham in the UK. And this is what we refer to as a HARPS-like. HARPS is a European very stable spectrograph that is kept in a vacuum chamber, and HRS on SALT is similar. So this is a vacuum chamber that keeps all the optics of the spectrograph inside here. And it's fed by optical fibers, and it's housed in an extremely high temperature stabilized room for stability to do very high precision radio velocity work. And it has different fibers that give different resolutions depending on what the science requirements are. So these are the three facility instruments. So by November 2005, SALT was ready to be inaugurated. There's a nice aerial photograph showing it. And at that time, all the telescopes at the rest of the plateau, but they've grown by about twice as much now, as you'll see from some of the photos I'll show. And the project has always been fairly high profile within South Africa, within the media, and also at political level. The Minister of Science was fully engaged with this. Anecdotal stories of Nelson Mandela bumping into the science minister and saying, "So how is SALT coming along?" You know, just shows at what level in government this was realized. And I think, you know, it culminated in the opening of the telescope. By then, Thabo Mbeki was the president of South Africa. So he officially opened it on the 10th of November. It was attended by 2,000 people, more than the whole population of Sutherland, actually. I don't know if Phil was at that ceremony, but it was quite an event. Had a fly past of the Air Force and so on. And it just, I think, was just an example of a project that had high support, high media attention, so much so that I couldn't resist showing you this lampoon in a local newspaper when there were conflicts between the president and his vice president, Jacob Zuma, who's sitting on top of that dome. And I think it's the first time I've ever seen a telescope used in political commentary, but it just showed you how higher, you know, in the minds of South Africans this project was. So I'm going to start moving on to, because I see I've got, is it 7 minutes or hopefully a little bit more than that left to talk about some of the signs. And I can't talk about all of the signs because there's just so many different things that our different partners in SALT are doing with this telescope. Everything from solar system astronomy right through to looking, well, you know, things like gamma ray bursters, the most violent events in the universe. And also we had a big role in the follow-up of multi-messenger observations of the gravitational wave event, GW 170817. So the one thing that I'm focusing on, and I'm the PI for, is the SALT Large Science Program on transients. And transients are, I think probably you all know, anything really that goes bump in the night. So it can cover things from the closest to the furthest. And so the transient universe is something that really over the last decade or so has come, come to the fore. The fact that there are so many different facilities worldwide probing the universe and finding transient behavior, variable stars, variable behavior, which sometimes is unpredictable. And so some of these we're, I think, quite familiar with, like the Gaia mission, this wonderful European Space Agency satellite that's mapping over 1 billion stars in our Milky Way, is finding many different transients as well. And so we have been using SALT to follow up these and study them in detail to know more about their physical behavior. And so the SALT Large Science Program began in 2016. As I say here, it's paving the way to the next big transient discovery machine, which is the Rubin Observatory, which is the legacy survey of space and time. So at Sutherland, we have actually our own transient detection facilities. We have this Russian facility that's been operating since 2015, fully robotic, and since 2018, MELICT. And these are discovering optical transients in their own right, but we're following up any sources at all. And so we have a wide collaboration, over 30 co-investigators, including about a dozen graduate students, covering basically anything that you would consider to be transient, from extragalactic objects to, like in the active galactic nuclei and so on, supernovae, gamma ray bursts, and more recently, the things in red here, multi-messenger sources like gravitational waves, neutrino events, and radio transients with the new radio telescope. And this plot here just shows one of these transients that became really famous because of the fact that we were one of the first telescopes to get a spectrum of this event 1.2 days after it was discovered. But in terms of, the sort of phase space of the energetics of these objects, it covers some of the most luminous, energetic things in the universe to more sedate things like flare stars and X-ray binaries and so on. So this is one project that I was involved in last year. We finally got our paper accepted on this, which was a nice example of serendipity where SALT could follow up a gamma ray burst that was very bright. Usually gamma ray bursts don't get to be too bright. This got to be 10th magnitude. And then they decline very fast. Typically over a few hours, they're no longer visible. They're too faint. In the case of this one, because it was so bright, we were able to get onto it with SALT a couple of hours after it was first discovered and make important spectropolarimetric observations, of which there's only one other GRB that's ever had spectropolarimetry done. So this was being at the right place at the right time with the right object. More recently, with the high resolution spectrograph, an ex-student who's now actually a Hubble fellow, recently appointed at Michigan State University, has been working on novae and using the wonderful high resolution mode of SALT, the HRS, to get detailed profiles, emission line profiles from novae. And this is an example of a system which was a really important discovery in nature astronomy, where it was discovered that it showed outbursts in gamma rays coincident with optical, which had never been seen before. And then my own work focuses mostly on X-ray transients, which are high mass and low mass X-ray binaries, which can have either neutron stars or black holes accreting from a sort of more normal solar type star here. So here's an example of an object which is a black hole transient, which happened to go through an outburst in 2017 and 2019, both observed by SALT. And what we discovered was these sort of dips. These are light curves showing the intensity of the object. And you can see there are sort of, not periodic, but you can see there's dips on timescales of a few hundred seconds, which actually evolve. They get to be longer timescales as the outburst goes on. And it's attributed to a very obscured black hole accreting system in the middle here, where the inner part of the accretion disk has these vertical extensions that periodically eclipse or block the light coming from the inner engine. And because the material on the inner edge of the disk is rotating at about a period of 100 seconds, that's why the dips we see are happening at 100 seconds. And why they go to longer periods is because these structures are actually driving out into the disk. And as they move out in radius, they go to short, much longer periods. And so the dip frequency decreases. And then more recently, some of the work on transients with SALT has centered on following up from X-ray transients discovered by this new facility called eRosita, a German Russian mission to map the whole of the hard X-ray sky over a period of 4 years, which sadly is now in a state of, well, it's sort of put into a safe mode while this problem with Russia is ongoing. So there's no data coming from eRosita right now. But what we did discover with this was unusual galaxies that show quasi-periodic eruptions. These are sort of light curves here showing these eruptions in X-rays, which in these two galaxies that were observed by SALT show periods of 18 hours in one and 2.5 hours in another. And unlike anything else seen before, the galaxies are sort of red and dead. They're not active galaxies like we're used to, what we call AGN, where there's lots of ultraviolet, lots of X-rays being produced by a central black hole. These galaxies are very dull galaxies. And so what they're thinking to explain this is that the X-ray, quasi-periodic X-ray outbursts from these galaxies is not driven by the same thing that's happening in AGN, but more like the black hole in the center of our own Milky Way, which might accrete stars from time to time. In the case of this, it's thought that a compact object orbiting the supermassive black hole is responsible. So this is a sort of new discovery. Right, I'm on the home run now, so I want to finish up with talking about future developments and some things somewhat outside of just SALT. And one of them is this project that we call the Sao Intelligent Observatory. And the aim of this is to roboticize many of the telescopes that we have. I mean, some of them already are robotic, like the Las Cumbres Observatory, but some of the older ones are not, like the old Radcliffe telescope and the 1 meter telescope. But we're now moving to do this, and in fact, not long ago, succeeded in having fully robotic operation of a telescope that had never been designed to be operated in that way. And why are we doing this? Because there's going to be an enormous challenge for following up transients in the era of the Rubin Observatory. So our aim here is to build something that will be an automated follow-up machine rather than something that requires human intervention to make the observations. And it will potentially involve about 11 of the telescopes at Sutherland, including SALT. And work began on that in 2020 and is progressing really well. It involves linking together outside alert systems from telescopes, even satellites like the SWIFT satellite here, and then sort of making automatic decision-making on what appropriate follow-up observations should happen. And this involves using software already being developed, for example, at the Las Cumbres Observatory, things called target and observation management tools, which are becoming very popular for automated follow-up. And so some of the facilities we'll use are already robotic, like these two telescopes here. The Monet telescope is one owned and run by the Göttingen University in Germany. This other telescope, Lesedi on the right, is a new 1 meter robotic telescope. Here we have Meerlicht, which is the most recent 0.65 meter wide field telescope, which has been designed to follow up radio transients discovered by the Meerkat array of radio dishes, which is in Carnarvon, another 300 and odd kilometers away from Sutherland. This is a 64 dish, the most sensitive mid-frequency radio telescope in the world now, and will be part of phase 1 of the square kilometer array once it's built. And then finally, there's a new telescope that I've been involved in called PRIME, which is primarily a Japanese-US project. We have been responsible for providing the building And this is an infrared telescope, which will have a wide field of view. And its main science driver is looking for microlensing events caused by exoplanets. And but one of the things that it will do is also follow up infrared transients. And all of this is feeding through to these facilities that we will use in following up the huge amount of data that will come from this, which is the Rubin Observatory telescope, which will be conducting this 10-year survey beginning sometime in 2024. And South Africa is involved in this follow-up. And one of the things we're hoping to do is to develop the software to allow US participants in LSST to access our telescopes. We're providing a certain fraction of time on both SALT and smaller telescopes for the US community to follow up science or to follow up transient discoveries. And then finally, I just wanted to mention the sort of expansion of the SAO's Intelligent Observatory into a new project, which is just beginning, called the Brics Intelligent Telescope and Data Network. For those of you who don't know, Brics is a consortium of countries, Brazil, Russia, India, China, and South Africa. And it's a sort of economic, if you like, block, but it has many other goals, of which science collaboration is one of them, and astronomy in particular. So all of these countries, as you know, have their own facilities. And the idea for this is that we will link, network the telescopes within all 5 Brics countries to build a similar intelligent telescope machine to the one that we will have in South Africa for transient follow-up. And then a far more ambitious second phase would be the development of a worldwide network of about 70 1-meter telescopes with very wide fields of view, 25 square degrees, distributed over the whole globe, which would allow all the sky, the entire sky, to be photographed about once an hour, which would be a huge game changer in the discovery of fast transients. A very ambitious program. And to be honest, it's really being driven by the Chinese, who want to see this as a sort of strategic future project in astronomy. So I'm going to finish now just with one other slide to say that similar ideas are happening in Africa. There's a revamped African Astronomical Society, which has aims to develop science collaborations and to work together. One of the things that we've come up with is the idea of what we call African Integrated Observation System, where we bring the different telescopes in Africa and work together on collaborative projects, and even to try and automate the sort of observational methods between the observatories. So that brings me to an end. I just make these final remarks that you know, the road to SALT has been a long and interesting journey. I haven't told you some of the problems that we had to solve along the way. I just didn't have time for that. But given the fact that this project team came with like no previous experience and you know, did this job, built this telescope to budget. It was built for $19.8 million US. It met the original budget. I think is testament to success. And I think, you know, one of the reasons that the Meerkat telescope and the SKA is going to be built in South Africa, at least the mid-frequency array, is because of the demonstrated engineering prowess that South Africa has demonstrated initially in building SALT, and now, of course, building Meerkat as well. So yeah, I think that brings me to an end. Yes, I'll leave it at that. And if there's any questions now, I'm quite happy to answer them.
Thank you. Thank you very much, David. Can you stop sharing the screen so we
Yes.
see everyone? Yeah. Okay. Thank you. Let me see from the chat line first.
Oh, I can see some of them myself. Yeah, I'm looking.
Okay. So the first question is, can you direct me to detailed design information for your polarimeter? That's from
Tony Mikesell.
Tony Mikesell. Yeah.
I can certainly do that. There's a couple of papers within the SPIE, which I'm sure you're familiar with that journal, which discusses the whole design of the Roberts-Tobie spectrograph, which Ken Nordsiek was the PI, as I mentioned. So yes, there is certainly papers I can point you to. I should mention that the design of the polarimeter was quite challenging given the optical design of the telescope, simply because of the fact that you have a segmented mirror, which is not symmetric because the pupil is not symmetric. But nonetheless, Ken Nordsiek, he's a proficient polarimetrist, and he sort of showed through sort of simulations what we could achieve with SALT for polarimetry, and they've essentially been delivered. I mean, we use the polarimeter mode, spectropolarimetry mode, quite extensively. I showed the results for the GRB, but we've also looked at other objects as well with the polarimeter quite successfully.
Okay, another question, I think also from Tony. Dina, you have something?
I was just going to recommend that if you could, Dr. Buckley, if you could put a link to that information in our chat for Tony, that might be helpful. Or if you want to send it to Mehmet later, we could forward it to him.
That would probably be easiest because I'd have to go and browse my folders to find it. I don't have it at the top.
Okay.
But I can definitely send the links and maybe PDFs of the papers themselves. Yeah.
Wonderful.
Just send them to me, David.
Yes.
Thank you.
Tony is also asking, I think, how is masking of unwanted light achieved?
Yeah, good question. Yes, so we have a moving, in fact, can I share my screen again and I'll just go back to the relevant slide.
Go ahead.
So I'll have to. Are you seeing it? You're seeing the last slide, I suppose.
Yes.
Yeah, it's not progressing. Oh, hang on. Here we are. Yeah, so there is something called the entrance pupil, which is actually on the surface of the primary mirror. It was in that simulation that I showed of how the tracker work, which I'm slowly going back to. It is the sort of hypothetical region which, well, it's not hypothetical, it's the real region where light that falls on those mirrors will end up at the instrument. And yeah, so you can see here, this is the pupil. And so the pupil's actually 11-meter circle. So it would carry on around here. And in fact, if, just for argument's sake, say an astronomer was on the observing floor with a flashlight down here, and they shone it up, that would actually enter the instrument. So we have to baffle that stray light. And this is done over here. If you can see on the left, here's a little moving baffle that has the same cutout as the primary mirror array. And so this baffle is the thing that cuts the stray light from entering the pupil here. Does that answer it?
I think it should, yeah.
Yeah.
Okay. Okay, let me go back. Okay, next question here is Don Lin. Why did SALT settle for less than diffraction limited in its mirror alignment system? Wasn't the technology available from Keck?
Oh, it certainly was available from Keck. Yeah, that's a very good question. Basically cost and basically lack of infrared instrumentation. So what Keck tries to do, or does, succeeds, is what's called phasing the mirrors. And so they have a phasing camera that can align the mirrors to an integral number of lambda over 4 so that you have coherent adding of the wave fronts. And that means that you can then get the diffraction limit of a 10-meter telescope. And the driver for that is, with adaptive optics, you can remove the effects of atmospheric turbulence that degrades the images due to seeing, and you can then achieve the diffraction limit with a 10-meter telescope if you do the phasing of the primary mirrors. The phasing puts demands on the fact that you need a phasing camera for a start, but also on the mirror edge sensing system to allow you to be able to know exactly how the mirrors are offset from each other. That latter part is not so difficult with the edge sensors we now have in SALT. They have the resolution to know that. However, there's no reason to do the correction unless you have an instrument that is working in the infrared at the moment, you know, an adaptive optics instrument. So adaptive optics is expensive. It also is not necessarily the same solution at a given site. So in Hawaii, for example, where the conditions are excellent, or Chile, adaptive optics has a huge benefit. At our site, which is a sort of continental site in the middle of South Africa, I guess similar to HET actually in Texas, the potential of getting very good quality adaptive optics correction is far more challenging. But really it came down to cost and not having any way, you know, we wouldn't be able to develop an adaptive optics system within the budget of the telescope. Furthermore, there was a lot of work that was needed to be done to characterize the site to know, you know, how good is it, you know, how good a prospect would it be to do adaptive optics? I actually had a student who, she's now working as a postdoc on the Gemini telescope, who for her PhD did an investigation on the prospects of this. And our conclusion was, certainly in the region that we operate, which is out to, you know, like 900 nanometers, 9,000 angstroms into the beginning of the near infrared, there was no real advantage, even for a simple ground layer adaptive optics system. Plus the fact that you've got this whole moving prime focus region. So all of your adaptive optics correcting mirrors would have to move with that. So it's never really taken off, other than, you know, the sort of original concept idea that the student of mine investigated.
Okay. There are quite a few comments here thanking you for an excellent presentation. One comment actually is from Michael Gardner, says that they have been to Cape Town and loved it.
I saw.
And
Yeah, I saw
combined
his
the
comment.
archaeology with astronomy.
That's very interesting. Yeah.
Yes.
Yeah, I know the Cedarburg Observatory very well because, in fact, we have a sort of holiday cottage in the Cedarburg. And so we go up there from time to time. It's the middle of nowhere. It's like a real wilderness area. And it's absolutely beautiful skies there, I must say. Yeah. So I bet Michael had a nice time at that place. Yeah.
Yeah. Are there any questions that people want to raise? Please raise your hand and or comments, for example. Phil, do you have any comments?
Oh, I'd just like to thank David. That was an excellent presentation. And it brought back a lot of good memories on how these big telescope projects evolve. They're ongoing technological, they're just as much technological development projects as they are astronomical development projects. So yeah, that was really a lot of fun to listen to it, David.
Thanks, Phil. Yeah, I mean, I remember fondly, the meetings that we'd had in Austin. I mean, I've got photographs, taken in like restaurants and bars, and
I think we had a
I'll
good
have
time.
to share some with you sometime.
I noticed that in some of the pictures, your beards were dark, black. What happened to it?
Yeah, well, that's very good. In fact, just let me quickly share something else with you because you might be amused about this. This was a talk that I gave to the 50th anniversary of Mount John. So this is. Are you seeing it?
Yes.
So this is me when I was a master's student in New Zealand. So you can see how my beard or how my albedo has changed from, from that time.
Nice. Almost unrecognizable.
Almost, yes. Well, I'm wearing a big Russian hat as well, so maybe that's also partly the reason. But yeah.
Okay. Any other questions, comments? Dina, do you have any comments?
All I can say is I use hair dye to keep my albedo from changing.
Well, I have to tell you something, Dina, that I was persuaded for a Christmas party at the SAO in 2008, I think, that they wanted to have a Christmas party in the theme of the Academy Awards, pretending it's the Academy Awards. So they asked me to be the MC for this. Now, at the time I looked pretty much, maybe not quite as white, but certainly not dark. And I had a much bushier beard. So I actually shaved my beard off, dyed my hair, and wore a tuxedo and dark glasses. And no one knew who I was when I walked in and walked to the front before I started the ceremony.
Oh, I can imagine.
Since we don't have any more questions, I guess we can stop the live streaming. Are there any other questions? One last time. No, I don't see any. So we can stop the live streaming and